All right, let's just jump right into it. Have you ever looked at your network settings and wondered what those different 5G toggles are actually doing to the physical infrastructure around you? Well, today I'm putting on my senior telecommunications architect hat to walk you through the massive architectural dance that picks off every single time you tap one of those buttons. We're going to peel back the screen of your smartphone and look at the exact cellular mechanisms running the show. Take Smart 5G, for example. What's really happening when you toggle that on? You might think, oh, it's just a neat little battery-saving software trick. But no, it's actually triggering this wildly complex chain of protocol state transitions and core network rerouting. It is a highly dynamic, real-time negotiation between your user equipment, your phone, the radio access network, and the core network. So here's our roadmap for today's explainer. We'll hit deciphering 5G user modes, RAN and core dependencies, 5G voice and fallback, RRC states and transitions, scaling with O-RAN, and finally, cognitive radio optimization. We're taking a top-down approach, starting right from the device in your hand, all the way to the absolute cutting edge of cognitive radio research. Okay, Section 1. Deciphering 5G user modes, the interface. Let's set the baseline. 5G standalone, or SA, operates completely independently. We're talking maximum speed, incredibly low latency, literally the pure, true 5G experience. But then we have 5G non-standalone, or NSA. This uses 5G for the actual data transfer, sure, but it still heavily relies on your older 4G core infrastructure to function. We saw NSA everywhere during the initial 5G rollouts just to get the tech off the ground fast. And that brings us to your phone's actual settings: 5G preferred, 5G only, and Smart 5G. Now, as a network architect, I don't look at a Smart 5G toggle and just see a UI button. I see a literal command telling the network to rapidly juggle control planes and user planes, dynamically shifting between those NSA and SA pathways we just talked about. And it's doing all of this just to save you a few battery percentage points without dropping your latest download. It's wild. Let's look at how the network physically handles this. Moving on to Section 2, RAN and core dependencies, the network engine. Okay. Check this out. In NSA modes, your data is routing right through the legacy 4G evolved packet core, the EPC. The radio access network architecture here is using a master ENB, that's your 4G LTE base station, paired with a secondary GNB, which is the 5G base station. They connect to each other via the X2 or XN interfaces, depending on your specific deployment. Basically, the EPC acts as your anchor. The 4G node handles all the control plane signaling, while the 5G node steps in to do the heavy lifting for the user plane data. Now, contrast that with pure 5G SA mode. When you toggle to SA, you are completely bypassing that legacy EPC. Instead of relying on S1 MME and S1U interfaces to constantly talk back to a 4G core, a device in SA mode communicates directly with the 5G core. It uses the NGC interface for the control plane and the NGU interface for the user plane. It is a drastically more streamlined, fully autonomous connection. Which brings us to Section 3, 5G voice and fallback, the call continuity problem. So what happens if you lock your phone to 5G only, but your carrier doesn't actually support Voice over New Radio, or VoNR? Well, traditionally, your phone calls would just break. No way around it. To prevent that absolute disaster, the network initiates a highly complex procedure known as EPS fallback. Essentially, the network has to rapidly shove your connection all the way back to the 4G core just so you can use standard Voice over LTE. Just think about the sheer coordination happening here. Your device is literally forcing the 5G core's access and mobility management function, the AMF, to rapidly select an MME node in the 4G core just to keep your call alive. The 5GC forwards your device's exact context to the EPC and instructs the GNOBead to set up a dedicated voice bearer. That is a massive amount of signaling firing off in mere milliseconds, all so you can order a pizza without the line going dead. All right, Section 4, RRC states and transitions, shifting gears. Here is where Smart 5G really works its magic. Instead of fully disconnecting you the second your data stops flowing, it utilizes the RRC inactive state. It deliberately suspends the 5G core connection to save power, but here's the kicker. It stores your user equipment context right there in the NG RAN and on your device. So when you need data again, boom, you get a lightning-fast resumption back to RRC connected, completely bypassing the heavy battery-draining signaling that would be required if you were waking up from a dead RRC idle state. And this exact same logic applies to 5G preferred mode. When you walk out of a strong 5G coverage zone, the network seamlessly hands over your connection between LTE, which you see labeled here as E-Ultra, and 5G New Radio. The network is constantly, obsessively monitoring signal degradation and dynamically pushing your device through these specific RRC states. It wants to ensure you always have the best possible connection without needlessly draining your battery. Section 5. Scaling with O-RAN. Artificial intelligence intervenes. Now scale all of this up to thousands of devices switching modes at once. It's chaotic. To manage those insane traffic surges, modern Open RAN, or O-RAN architectures, utilize RAN Intelligent Controllers, RICs. Think of RICs as the brains of the operation. They drop hierarchical reinforcement learning actors directly inside distributed units all across the network. By placing this AI right at the edge, the network can run localized, real-time resource scheduling based on exactly what the devices in that specific geographical pocket are demanding. And the results are huge. By introducing meta-hierarchical reinforcement learning, networks are seeing a massive 19.8% boost in management efficiency. How? By dynamically allocating resources across wildly diverse network slices. So whether you're demanding massive bandwidth for streaming 4K video on an eMBB slice, or you absolutely need ultra-low latency for competitive gaming on a URLLC slice, this adaptive weighting mechanism prioritizes those tasks instantly. It keeps the whole network rock solid. Finally, Section 6, Cognitive Radio Optimization, the future of dynamic access. Okay, so right now, smart 5G triggers its transitions based on a set of predefined rules. But with wideband spectrum sensing, we're stepping into the realm of true cognitive radio. This technique enables devices acting as secondary users to actively and autonomously sense sub-Nyquist wideband spectrums. They can literally hunt for and dynamically grab idle licensed spectrum in real time. They take whatever frequency is most efficient at that exact second without causing any interference to the primary users of that spectrum. It's brilliant. And when we combine federated transfer learning, or FTL, with cognitive radio, we can completely revolutionize how modes like Smart 5G or 5G Preferred operate. Instead of your phone just blindly guessing when to drop down to 4G, frameworks like FTL VSSNet allow the network and the device to preemptively adapt to spectrum scarcity using localized machine learning. And the best part? Federated learning trains these models right at the edge without ever exposing your raw user data. It makes these mode transitions instantaneous, hyper-efficient, and totally invisible to you. Which leaves us with a pretty fascinating thought. As a network architect watching these rapid advancements in O-RAN slicing and federated transfer learning, I truly believe we're hitting an inflection point. Very soon, this incredibly complex dance of core routing, fallback procedures, and RRC state transitions that we just explored will be 100% orchestrated by predictive AI. This cognitive evolution will likely rip the preferred network settings menu right out of your phone entirely, seamlessly giving you the exact connection you need exactly when you need it. So my question for you is, how much longer will we actually need to tell our phones how to connect?